Hello everyone, let's start today's class. So today we will be talking about testing, debugging, exceptions, and assertions. So far we have seen many different data types, how to define them, how to use them. We have also looked at the usage of functions. And so today we are going to see how do we test our code that we have written? What are the options for debugging? And what does it mean by exceptions and assertions in our program? So let's say you might have made soup many times. So what happens in this scenario is that you're making soup, let's say, but there are bugs that keep falling from the ceiling. So what do you do? There are a few options. You can, first of all, check how many bugs have already fallen in, check your soup and try to take them out. But you can also keep the lid closed of the pot so that no more bugs fall into that pot of soup. But also you can try to clean your kitchen so that there are no bugs that might fall in your soup. When we relate this to programming, checking your soup for bugs means you are testing your code, and keeping the lid closed would be analogous to do some defensive programming so that no bugs are introduced in your code. And cleaning the kitchen would mean that you are eliminating, you have debugged your code, you have found where the bugs are originating from, and then you eliminate the source of those bugs. Okay, so let's move on. Let's see what all of these terms mean. So defensive programming is a good technique, and what this means is you should write specifications for the functions that you define, so that any other programmers who are using your functions, they know what kind of inputs they should provide and what kind of output they can expect and what the function does for them. That would also mean that you modularize your programs. You divide them up into functionality that does something separately, and define each of them as functions, so that each of those functions can be tested and debugged individually. And once they are working, then they are working in all instances wherever they are being called or invoked from. And lastly, you should check the extreme conditions on your input and output. Make sure that if you are expecting integers as the input to the function, in the beginning of the function, you use the assert statements, and we will look at them at the end of this lecture to make sure that the input is what you expect it to be, so that there are no issues in the computation that you are going to do in that function. So one part of it is testing and validation. So compare the input and output, make sure that they match the specification of what you are expecting, and think about if it's not working, why is it not working? And then during testing, also think about how you can break your program. Are there any scenarios of sets of inputs that can cause your computation or your statements that you have in the function to break the program? On the other hand, debugging would mean that you come across a bug, which means something, the program or your function is doing something that it is not expected to do. So you study the events that cause it, and you find out why it is not working. And once you have found that, you can then start to think about how you can fix that issue or that error. As a programmer, you should think about um, how you will. So you can program. Anyone can write a program, but writing a good program is the key here. And from the beginning, you should design your code to make it easy for you to test it and debug it. One method to do that would be to break it up into smaller modules that can be tested and debugged individually, which we have looked at functions, for example. So don't write one long, lengthy program that just runs in sequence. Instead, break up your functionality and encapsulate them into smaller functions that you can then test and debug individually once they are working for all of the conditions, all of the partitions of input, and all of the extreme conditions, then they should always work. Secondly, you should document your constraints. For example, what kind of input you are expecting, whether it's a number or a string or a list, and at the beginning of your function, check for that. Um, and what do you expect your output to be? Document that in the doc string at the beginning of the function so that whoever is calling it, when they get back a result, they can check for it. And you should document all the assumptions behind your design, behind your code, or whatever your implementation is expecting. Document all of those assumptions, and they can also be documented in the doc string at the beginning of your function. That's a good programming practice. So let's say you have written your program, your set of functions, and then what do you do? What do you do when you are ready to test whether it works for all the situations and all the conditions? First of all, make sure that your code is running. When you call the function, it doesn't break, doesn't give you an error message. It parses correctly, which means if there are any syntax errors, you should remove them. If there are any other semantic errors, you should remove them. And all of these, if your code is not written properly, whichever IDE or programming interface you are using, they can probably test it for you, and they can let you know there is a syntax error or there is a semantic error. So these are easy, but then also for your testing, you should have documented your expected results and then define an input set. Okay, I will test it with these sets of inputs, and these are the outputs that I'm expecting. Is my function doing this properly or not? There are different classes of tests, different types of testing that is done at various in the timeline of the overall writing of your program or your functions. First of all, there is unit testing, which means that you validate each piece of a program or each function separately. And once you have done that, you can, if you find any bugs, you should add specific tests to test those bugs again. You go back and fix it, and then try your unit testing once again, come back to regression testing, and the tests that you have already defined, they should pass this time because those you have fixed. There may be other errors, or maybe as part of the fix that you did, you introduce some new errors. So regression testing would be a cycle between regression and unit testing, and you would fix errors, you would go back, start from the beginning of the testing, and then see if everything works okay. So once you have done that for several functions in your code or in your program, then you are ready to do integration testing, which means that does the overall program work? Okay. And that would also be a cycle. If everything is fine, then it's okay. If not, then go back to your unit testing, see which of the functions are not working properly. Go through the cycle of finding the bug, fixing it, and then coming back to integration testing. When it comes to programming, programmers tend to write everything and then try to run everything at the end once. But it's a good practice to do unit testing for each of the functions that you have already programmed, and then do regression, and at the end do integration testing to see that all of the function calls that you have for all of the functions that you have defined, they all work properly, based on the set of inputs and outputs that you are expecting. So there are a few testing approaches. First is intuition, that you have some kind of documentation of what a function should be doing, and that is defined as the doc string at the beginning of the function. So this is a function that tells you whether the number x is bigger than y or not. Okay, so it assumes that x and y are integers. That's an assumption that we have for our inputs, and returns true if y is less than x, otherwise it would return false. Okay, so what are, can you think of some natural partitions, for example, for the inputs that you would be receiving here? Maybe you can say it's they're all integers. So maybe if x is less than y, then what happens? If they're equal, what happens? If y is less than, what happens? And all of those partitions or scenarios, you should be doing your testing about that. You can also do some random testing, but that's not kind of a complete or for sure kind of scenario where you can make sure that everything works properly. There are two more methods that are methodical in terms of how we use them. One is called black box testing, where you explore all the paths, but only use the specification which is defined at the top of the function or as part of the documentation of your function. You don't have to, or you should not look at the code of what it is doing, but just based on what inputs are defined, and what is the expected output. You give the input using all of your scenarios and see whether you get the expected output or not. That kind of testing is known as black box testing. Second is glass box testing. That means that you have access to the code of that program or that function, and then you go through all the paths and make sure that your testing covers everything. And the way to do that would be to look at the code itself. Let's take a look at an example of black box testing. This is a function that is getting you the square root of a number x using an allowed error value of epsilon. So it says that x, epsilon are all both floats. X is greater than or equal to 0, and epsilon is greater than 0. Okay, and it returns you a result such that the result times result, or the square of the result, is between x minus epsilon and x plus epsilon. Okay, so now the kind of test cases that you would define to test this function are just based on this specification. When you are doing black box testing, you would define your test cases without looking at the code. And this can be done by anyone other than the implementer, and this preferably should be done by someone else, because implementer bias is a real kind of thing in programming. When you have written something, you always find reasons to justify scenarios, but someone else might take a look, might be looking at them differently. So if the implementation inside the function changes, but your specification does not change, you can still use the same set of test cases that you defined earlier. You might rewrite the whole function to be a little bit more efficient, but the testing would not be different than what it was before if you're doing black box testing. So you define the paths and you define your test scenarios, and then you do the testing on that. And in this case, you should also always check the boundary conditions, which means the conditions on the edges of the scenarios. For example, what happens if you receive an empty list? What happens if you receive a list with just one item? What happens if you give it a really large number or a really small number? So here, for example, there is there is some kind of planning which is done as part of testing this function. You have a boundary condition where you pass it x as 0 and epsilon as 1. You can try your answer with a perfect square. Do you get a proper answer or not? What happens if you give it a value less than 1? Is your function implementation calculating that correctly? What happens if the square root is irrational? What kind of result do you get in that case? And then there are extreme scenarios. For example, give it a value of x between 1 and 2 raised to the power 64, which is a really large number. And then your epsilon is also on the extremes of those allowed scenarios. And then a combination of all of these. So this would define the plan for your testing based on black box testing. Glass box testing, on the other hand, is using code directly to identify or let you plan the test cases since you have access to the code. And these are path complete test cases, which means you make sure that all the paths within the program, all the statements, all the loops, all the if conditions, they are tested at least once. Uh, but there are still some drawbacks. This is also not a perfect scenario. When there are branches or loops, for loops or while loops, there are many different scenarios of how they will be executed when you are going through the testing of this program. And what you have to make sure that if there are branches, which means you are using if statements, and design your test cases that go through all the parts of those conditions. It go through all the if, and the else condition in those branches. For loops, you should make sure that what happens if the loop is not at all entered, which means the condition that is defining the logical end of the loop, if it's false already, when you reach it, what happens in that scenario? What happens if it's executed only once? And what happens if it is executed more than once? And if you cover all of these in your glass box testing, then your the result of your function is okay. Then it means it would eventually be working fine. So here's an example of this function is returning the absolute value of a number, of an integer. Okay, so it is assuming that x is an integer and returns x is if x is greater than or equal to 0, and returns minus x otherwise. Because if it is already lesser than 0, it would be a negative number, and if you negate it once again, it would become the absolute or positive value. So you say if x is less than -1, then return minus x, else return x. But this code is not correct. It's buggy. It has a bug, and the bug is that if you call it with the number -1, it would give you a wrong answer, because there should probably be x is less than 0 here. Or if you're just dealing with integers, it should probably be less than or equal to -1. Okay. So this would be one of your conditions that if it's not included in your testing, you would miss this bug, and there would be problems when this is being used later on. So here's an example. In 1948, this computer or calculator, let's say, was created, and this whole room and all the machines that you see, it's one really large calculator that could do addition, subtraction, division for you. And this, in some cases, it wasn't giving the correct answer. So they kept on checking everything. They kept on checking all of these big boxes. There were relays and panels in them. And what they eventually found that through their methodical checking, they found that in panel F relay 70, there was a bug, and this was this was an actual bug. And you can see they wrote a note here in their logbook that first actual case of a bug being found in your code. So so took the bug out, put the relay back in, and it started working properly. So that brings us to the topic of debugging. So far we have talked about testing, how to test a program, but what happens when you find a bug, when your test fails and you identify where the bug is. So debugging is kind of a steep learning curve. One has to be a programmer to be able to debug a program, and your goal in this process of debugging is to have a bug-free program. All right, so there are many different methods or tools available to you to enable you to do debugging. First of all, debugging is built into many IDEs, including IDLE and Anaconda or Spider that we are using. You could also use Python tutor to see what are the values of the variables, how the frames are set up as you go through the code line by line. Um, you can also use print statements. This is a very basic kind of thing that you do. It's not difficult. You can print the value of any variable anywhere in your program and see what the value is, and is it what you expected it to be. And sometimes it is very, very useful. I also use it a lot. This makes understanding the working of your program very quickly and easily. And lastly, you can be a little bit more systematic and do your debugging that way. We will take a look at all of these separately. So let's talk about print statements. How do you use them? Should you use them? It's printing the values of variables, printing the values of inputs as soon as you come into a function is a good way to test that these values are matching your hypothesis, which means these values are matching what you expected them to be. You can print that you have entered a function. You can print the values of the parameters, and then you can print the return value just before you call the return statement. So that would, as you run the program, you would see those in your output, and you would be able to identify if it is working properly or not. If your program is a little bit longer, you can use bisection method. For example, put the print statement somewhere halfway in the code and see if the value matches what you expect it to be. If it is okay, then print something once again in 3/4 way of the code, and that way you would be able to reach the part of your code quickly where the bug is located, where the values that you see in your print statements do not match what you expect them to be. So the steps that we follow in debugging the program is to study the code, and um, um, you of course you want to know what is wrong, but what you really should be looking at or trying to find out is that how this unexpected result or this wrong calculation happened. And that's actually what you are looking for. And when you find it, you may also think about, is it something that is written, is this part of the code which is written in a way that may produce more errors. So when you fix one, you fix all of them. But at the same time, you can use the scientific method as well, which means you study the available data, you form a hypothesis based on the all of the inputs that you might be receiving for this function, and then write your tests based on that. You should write your tests which are repeatable in some manner, so that once you fix something, you do all of those tests once again, and see if the fix was good enough. And when it comes to error messages, as part of your execution of your code, there are many different error messages that Python throws towards you. We will take a look at some of them when we look at code example. For example, here this is an index error when you try to access an index within a list which is not present. If your list is 3 element long and you try to access the fourth one, you would receive an index error. If you try to convert something into an integer which is not a number, you would get something which is called a type error. If you try to reference a variable which is not present, which you have not defined or initialized, you would get a name error. And in the very first lecture, we saw this example as part of data types, that if you try to combine an operation with two data types which are not compatible for that operation, you would get a type error. And simply here, this is a syntax error. Your program won't even run before you fix all syntax errors. And here, this closing parenthesis is missing, and that was the syntax error in this statement. Logic errors, if there are no syntax errors, no semantic errors, but still your program is not doing something that you expect it to do, it's not giving you the right result. Finding and fixing those logic errors are really sometimes really hard, and uh, it's probably good to take a break, go somewhere, come back after some while, and maybe you will look at something that you were missing before. Another very good method to find logic errors in your code is to explain the code to someone else, preferably someone who does not know programming, so that you have to explain everything. And as you are explaining, you might find the issue that you were missing before. Rubber ducky debugging is a real real thing. You can check it on Wikipedia. This is really something, explaining the code to someone else, but they are not talking back to you or not really understanding. But you are going through the exercise of explaining the code to, in a way, back to yourself, and that way you might come across the logic error that you were not finding before. Let's take a look at some of the do's and don'ts for writing good programs. Um, People tend to try to finish the whole specification of a function or a program at once and then test the entire program or debug the entire program. That's not a really good programming technique. What you should do is write one function, test and debug that function, write the second one, test and debug the second function separately. And once all of these are working individually, then do your overall testing. Okay. Um, when you are in the process of doing a long assignment or writing a long program, you may change your code, and it's always good to have backup when your program is in a good working state. Make a copy, keep it somewhere, and then do the change. It's at that time you might think that, oh, I know, I remember, I will remember where this bug was, and I will come back to it. But as you go along, changing your code, enhancing it, it's sometimes you lose the overall picture. Instead, what you should do is back up your code in good working order often. You can then change your code, and as soon as you find a potential bug or a part of your code that you think might produce bugs, add comments in your code right there, and so that when you are coming back to it after many days, or even after working on something else, when you come back to it, you can read your own comments and understand what was going on here, and test the code in modules often. If you are still unable to find something, you can still compare the new version and the old version line by line and see what kind of changes you did. Now let's come to exceptions and assertions. So what happens if an error occurs? What happens in Python is that it throws an exception. By throwing an exception, it means it raises an exception which is something that that is returned to the user, that this kind of exception occurred. An index error occurred, or a type error occurred, or a name error occurred. So here, for example, you have a list of 3 items. If you try to get the fourth element, it's not there, you would get the index error. And an operation on 2 data types which are not compatible for that operation would result in a type error. And there are many other types. They are all documented in Python documentation. There could be syntax error, name error, attribute error, IO error. We haven't even looked at this. When you're reading from files, writing to files, there may be IO errors as well. So how do you deal with exceptions? You have written a program that doesn't work. In some cases, it works sometimes, but in some cases, depending on the user input, it breaks. So how do you handle them? For example, here we are asking the user to provide us a number, 2 numbers. What happens if they write their name instead of a number? You cannot stop them from doing it, and it's happens many times. Okay, so if we take a look at this code, which is not handling any exception, let's see how this behaves. So it's asking me to enter a number. I will give it um, the number 4 and the number 5. The answer is that a divided by b is 0.8 and a plus b is 9. So what happens if I give it 5 and 0? I get a division by 0 error here. Okay. And what happens if I don't even give it a number? I write 3. It's a value error. Okay. So we have these 2 errors, 0 division error and value error here. And we are not handling that as part of the implementation of our code. So one way to do that would be to use this try and except clause. So what this does is the part of your code that you think might cause an exception or an error, you put that inside this try statement. Okay. And then you run the code. If any error happens, it would come to this except clause, which means an exception occurred. And in that case, instead of showing this angry text here, which does not look user friendly, we can write something which makes a little bit more sense. For example, we will simply print that there is a bug in user input. And let's see what happens if we do this simple change to our program by simply writing these 2 statements and the operation inside a try statement, and then printing that there was a bug in user input. So if I run this time and give it exactly the same inputs that I tried before, 5 and 4, I get the answer. If I give it 5 and 0, it instead of giving me this bad looking angry text here, it's simply telling me that there is a bug in user input. And this is the print statement here in the except clause, which ran because there was an error in this calculation. It was trying to divide by 0. And lastly, the other example that I tried, if I give it something which cannot be converted to an integer, it would again be a value error, and it would go into the except clause and print the same statement. But we can be a little bit more descriptive of what kind of error happened here, and these are called handlers. So there are separate handlers for every kind of exception or every kind of error that happens. So here we saw in our example that we encountered 2. There was a 0 division error and there was a value error. We can show different types of messages as part of those specific errors being or occurring in our program. So instead of a simple try and except clause here, I am giving it multiple except clauses. I have a try statement which does something. our primary calculation, input and the calculation. And then I have 1, 2, and 3 except clauses. Two of them have a very specific error defined in front of them, and the third one has nothing in front of it, which means that if a value error occurs, then do this. If a zero division error occurs, then do this. And if anything else happens, then do this. Okay. And if we write our code that way, then we for all of those two bad inputs that I was trying before, I would get a separate or different error message. So let's say if we give it 5 and 4, everything is okay. If I give it 5, 6, and 0, error message has changed from bug in user input to can't divide by 0. And if I try to give it an input which cannot be converted, it would say could not convert to a number. So these outputs or error messages are now more meaningful for the user, and they know what they are doing wrong. And that has been made possible by using these specific except clauses for a specific error here, value error and zero division error. There are other options for using this try except clause. We can have an else within that, which means that this would be executed if try had no exceptions. So if the calculation was all good, and we had an else over here, that would be executed. And finally is executed every time as part of this try except else finally clause. And this is very useful sometimes to provide some cleanup code to tie any loose ends. For example, if you opened a file for reading or writing, at the end, just before returning, you should close that file. Otherwise, it would remain open and would not be accessible to any other function or any other user. So for that purpose, we use the finally clause as part of this try except statement. So what happens when we encounter an exception? In this example, we saw that we only printed what went wrong. We only printed that it's either a 0 or cannot convert to a number, but we didn't do anything about it. So what are our options if we try to gracefully provide some fixes within our code? So first option is to fail silently, which means you are trying to divide a number and the denominator is 0, and you decide as part of your specification that if that happens, I would just return 0 as the answer. It would work, but it's a bad idea because the user would not know that something went wrong, and they would be expecting something different, but you are using your default value for your answer. So it's not a good idea. Another option is to return an error value. For example, you have a function that says I will get you the value of the list in an index based on an index. If the value is not present, then my return value would be -100. But this specification should be mentioned in the documentation of that function, that if it returns -100, that would mean that the element is not present in the list. And that specific return value would have to be handled or checked wherever the function is being called from. So while it is a workable solution to return an error value in case of an exception, but it makes things messy and complicated when other people or other programmers are using your function. They have to make sure that they have a case for checking all the return error values. Third option is to stop your execution and tell the user that an error has happened. Okay, in that case, you would raise an exception and give it some descriptive string. And the method to do that, or the code, is that raise is a keyword, and then we have the exception name, and we have some arguments which describe, which has a descriptive text here that tells the user what went wrong. So out of these three options that you have when you encounter an exception or an error in your program, you can fail silently, default, substitute the input with some default value, but it's not a good idea. You can have multiple error values as your return types, as your return values, but this is also not a good idea because this makes using your function complicated. And last option is, which is more structured, is to raise an exception with something descriptive, so that the user knows something has went wrong, or the testers know something has went wrong, and then they would work on fixing it, either as part of implementation, or enhance their specification that our input should not be this or should not be that. So here's an example. We are trying to get ratios of two lists. I have a list L1 and L2, and they are of equal length. That's the specification. And they all have numbers. And it would return a new list. For each element, it would calculate L1 divided by L2. The element at L1 at the same index divided by the element in L2 at the same index. Okay. And my implementation is that I define a new list. I go through L1, and this index would be incremented every time. It would start from 0 and go to the length of L1 minus 1. And all I'm doing is, in this new list ratios, I am appending the division of L1 at that index and the L2 at that index. And I expect that in L2, because that's the denominator list, there may be some zeros in there in the input. So I'm trying to catch the zero division error, and I am appending this number called float of not a number, and this would return a reasonable value. This would not result in an error, and we will take a look at that example in code in a minute. And if the zero division error does not happen, but something else happens, then that would mean that probably in that list there wasn't a zero, but there was a string somewhere. So that would be a value error, and this simple text would be displayed to the user. So that way we can manage the flow of our program. Let's take a look at this example. Okay. So same code. I'm trying to get the ratios of all the elements of L1 and L2. And I'm trying to catch the zero division error here. And I'm trying to catch the value error over here. Else says that it is success. You remember else, we said that if try complete successfully does not go into any of the except clauses, then it goes into else. And finally would always be executed no matter what. And this is what it will print. Okay, so if I run this small program calling this function with one list being 1, 4 and the other list being 2, 4, our output is success is this printout over here. Executed no matter what is this one. Okay. So let's say if so this 0.5 is 1 divided by 2, and 1.0 is 4 divided by 4. Okay. Let's change the values a bit. Let's say I put a 0 over here, okay, which would try to divide 4 with 0. In that case, what happens is it said it didn't break, but it went into this zero division error, and it is providing me NaN, which means not a number. So when I try to divide 4 divided by 0, I get not a number as the answer. So it is exiting gracefully. It is telling me what it's doing. And at the end, it would still returning me something, and one of them is not a number. If I give it change this to a string, this 0 or any other number to a string, I would get a slightly different error message. And this is the actual error and value error. I'm raising an exception of type value error, and the description here is get ratios called with a bad argument. And this is the exact statement that I had over here. And that would mean that this should never happen, and program cannot exit gracefully, and someone should fix this problem. Okay, let's go back. Um, so one more example. Quickly, we're approaching the end of class time. We are given a list of, we have a list that has test grades. We have, as part of that list, we have multiple students. For each student, we have their name and another list containing the grades of their exams. And this is the second student. And we want to create a new list as part of our implementation, and we would return all of the same data, but also will add an average of all of the results that they have. Okay, and this is a simple implementation. Our function says get stats, it gets a class list, and all it's doing is that it is appending the element 0, which is the existing name, and then it has the element 1, which is the second item, and third item is it is creating itself, which is the average of element 1, and element 1 is a list of all of the grades. And this average function is returning the calculation of sum of all of these numbers, and then divided by the length of this string, this list. So it would add 100 plus 80 plus 74 divided by 3, and that would be the answer that would come here for the second person. So if we call this and there is a 0 as part of, if the length of the string, for example, for this student here, there are no grades. He was just sleeping at home, did not go to the classes, did not give any exams. Okay. So our calculation of sum divided by the length would result in a zero division error. Okay. And we should be trying to fix it. So the way we can fix it is that in our simple average function, which had only one statement, we add the try except clause here, and we say that do this calculation in the try clause, and if there is a zero division error, then print a warning that no, there was no grades data, and there is no return statement over here. Since there is no return statement as part of this except clause, the value that would be returned back is none. Second option for us is to change the policy that if there are no grades, then your return value should be 0. So the only difference between this implementation and this one is that we have added a return value in the except clause. So in both clauses, in try we have a return value, and in the except we also have a return value, and that would make our result a little bit more user friendly. In this case, this person who did not appear in any exam, the average is showing as 0.0, this number. If he did not appear, he or she did not appear in any exams. Last item for today are assertions. Assertions are a way to make sure, as the name says, that the assumptions that we did while entering a program or entering a function are true. We can add an assert statement. Usually we do it in the beginning of the functions to assert that the data types of the variables are what we expect them to be. For example, that's one example, and it's a good example of defensive programming, that your function would not even be executed if your assertion at the beginning of the function fails. Here's a very simple example for the same average function that was taking the average of these grades. Right at the beginning, we have an assert statement. And what it is asserting, or what it is trying to make sure, is that length of the grades list is not equal to 0. If it is, then it would say no grades data. That would be the print statement that we see on the user end, and the execution of the program would end right here. It would not go forward. So that's how the assert statements work. That if an assertion fails, we do something which is printing this message, and the program ends right here. But if this assertion is okay, which means length of grades is not equal to 0, it is something greater than 0, then the rest of the program would be executed. So assertions are a good method to do defensive programming. They halt the execution of the overall program. The program ends right there, and the user would not be able to give any bad input or move forward with the program. They are a good way to check the inputs to functions, because the function would not be able to work if the input is not of the specific data type or within the range that the function expects to be able to do the rest of the implementation, to perform the rest of the implementation. And they can also be used to check the outputs just before you return, so that you are not returning anything which would introduce bugs later on in the program as part of that value being used as an input to other functions or in other calculations later on in the program. So assertions are good supplement to testing. They make your code kind of foolproof. You would not be moving on in the execution of a program if an assertion fails within your program, and with the meaningful output result or a message, the user or the implementer would know where what went wrong. And the common uses for using assertion is to check the types of variables. You can check for constraints on values. For example, it should be between this and this, or would be of type this or something, and many other uses depending on what kind of program you are trying to implement. So that would be the end of the lecture today. Thank you, everyone. Take care. Bye.